Hello and welcome to this vodcast on topic 5 electricity and magnetism, in which we will look at 5.4 magnetic fields of electric currents, focusing just in this first part on magnetic fields themselves. So this is the final section of the electricity and magnetism topic, and it's a fairly brief one. Magnetic fields we'll look at this class, and then charges in a magnetic field will be the next thing we look at. So these are the subject guide sections on understandings, applications, skills and equations. And as you can see in this introductory section, we're just going to take a kind of basic overview of what fields are and particularly magnetic field patterns. So what is a magnetic field? Well, one definition would be a region of space where a magnet will experience a force, a bit like an electric field being a region of space where an electrically charged object will experience a force. Notice, and this is something we'll come back to, it will be a rotational force because a magnet always has two parts, which we call poles. Okay. Now, in reality, if you take a magnet pretty much anywhere, it will experience this force because magnetic fields are very pervasive. There are even galactic magnetic fields. Most things magnetic fields, though, are very weak. So we're just going to be talking about sort of dominant magnetic fields created by magnetically relatively strong objects. Although one of those objects that we experience is, well, the Earth. Because the Earth has a fairly strong magnetic field. That's how magnetism was first discovered, when some of the ancient civilizations, Chinese, the Greeks, realized that certain magnetic ores, as we would know them, if you shape them and place them, they will rotate to identify the north-seeking pole. So the north-seeking pole, if you take a magnet, it will tend to line up in correspondence to the Earth's magnetic field. Now, of course, the ancient people didn't know that the Earth had a magnetic field. All they knew was that these magnets, or lodestones as they were often called, lined up in a certain direction. They always had one end, if you shaped it in the shape of a needle or a bar like you've seen, was pointing towards the north. So that end was called the north pole of the magnet because it was the north-seeking pole, and the opposite one was the south pole of the magnet because it was always pointing to the south. So it would be the south-seeking pole. So this word magnetic poles, all magnets have two poles. It's a region, so the magnet has a magnetic field, and the magnetic pole is the region where the magnetic field is strongest, and the north pole of a suspended magnet will point towards the geographic north pole of the Earth. The south pole of a suspended or free to rotate magnet will point towards the geographic south of the pole. Now, if we take two magnets together, as these diagrams show on the right, and as I'm sure that you've been doing this since you were in primary or elementary school, then you'll find that pushing magnets with the same poles closest to each other will be repulsive. If you can't push them together, depending on how strong they are, you will feel a resistive force, a repulsive force. Similarly, if you take two south poles of magnets and push them together, you'll feel a repulsive force. On the other hand, if you take a south and a north, so that they are close to each other, close enough, you'll get an attractive force. So, as we've seen in previous units, electrically charged objects can repel or attract. And it's the same with poles. They can repel or attract. There are many correspondences, as we'll see, between electric and magnetic fields, poles, charges. There are also some differences. One of those differences is that poles do always come in pairs, or dipoles as they're called. So charges have two types, positive and negative, and although they're often found together, they don't have to be. Protons are purely positive, electrons are purely negative. However, that doesn't apply to poles. Wherever you have a north pole, you also always have a south pole at every scale. Now, to show a magnetic field following on from this idea of a north and south seeking poles of a little compass, a magnetic field will show you what would happen if you put a smaller compass or a smaller bar magnet in the presence of a larger bar magnet. You will get a north and a south. So the north pole, the north seeking pole of your tiny magnet, will follow these field lines. It will always point towards the south because it's attracted to the south. Similarly, the south part will be attracted to the north. So it will line up in this way. If you have a simple bar magnet, then the field pattern will look like these the blue lines at the top there. It always points away from the towards the south pole, away from the north pole. So the arrows show the direction in which the small rotating magnet will point. And if you have a simple bar magnet, as we've shown, you'll have the poles where the field density is strongest, which is shown by the lines being closer together. If you have sort of a north pole and a south pole from different magnets close together, then the pattern will be like the one marked B here. The unlike poles attract, the arrows join, the lines join the two poles. If you have two north poles, then that doesn't happen. The lines push away from each other. It repels. The south poles, two south poles, would look exactly the same, except the arrows on the lines would be pointing in a different direction, but the pattern of the magnetic field lines would be the same. So field lines, gravitational field lines, you've seen already. Electrical field lines, you've seen already. These are magnetic field lines. Like those other type of field lines never cross because they show a direction something's pointing in. It can't point in two directions at once, so they never cross. Also, please remember that this is actually a 3D effect. These field lines travel in all three spatial dimensions. What we're showing you here is like just a cross section, a slice through. One of the things before we move on, by the way, magnetic flux density is a measurement of the strength of a magnetic field. Exactly how that's defined we'll come back to later. But it does have a unit which we'll introduce now, and that unit is the Tesla, named after Nikola Tesla. It's a capital T. So, excuse me, the magnetic field simulator, if you follow this link, maybe pause and then copy down the address, will kind of demonstrate what I mean here. I can drag this little compass around, and always the red, which is the north seeking pole, points towards the south pole of the larger magnet. So these background little images here, the light blue, cyan, and red show sort of the field lines, and if you try and join up these red triangles, you'll get the field lines. Notice the fading away of the field lines indicates that the field is getting stronger. Weaker. The field gets weaker the further you get from the magnet. This video, again, there's the link for the video. Type it in to watch the full video. Let me just make sure it's not making any noise. It does have a commentary. So there's this stuff called ferrule fluid, which has got tiny, nanoscale magnetic particles. Strange stuff, very toxic, but irritant to the skin. So the guy here is pouring it into a glass bowl. Let's move on, and he puts it near a magnet, and you can see in the video the magnetic field lines create these really strange sort of spikes where the magnet is there, and you can see it's extending. So the magnetic field lines are coming out of the magnet here, and as he even gets close with that bowl, and he's got to be careful because it attracts. You don't want them slamming together. It shows these weird field lines. Apparently touching them is a really bad idea because it really does irritate the skin. Okay, anyway, it's a cool video. I recommend you go and check out the full length version. Now, we've talked about the Earth's magnetic field a bit, and we've also talked about the fact that the north seeking pole of a compass is attracted to a south pole, which does lead to a kind of unusual situation that can be a bit confusing. The Earth's magnetic field acts a bit like there was a big bar magnet in the middle of the Earth. However, that big bar magnet, which actually, if it was a magnet, be with its south magnetic pole at the north geographic pole. Because remember, our compass has that red triangle on the compass is called the north seeking pole, but north is attracted to south. So magnetically speaking, the geographical north pole actually has a magnetic south pole. The two aren't perfectly aligned, by the way. The magnetic south pole is not found at the exact north geographic pole, and in fact it kind of wanders around. It's rapidly leaving Canada as we speak and heading towards the Russian part of the Arctic. And similarly, the south geographic pole has a north magnetic pole which is wandering somewhere in Antarctica. But what actually causes magnetism? Now, there's a clue in the name of this sort of subtopic which talks about magnetism and electrical currents, because in fact the two are very closely linked. Here we have a demonstration as given by a man called Michael Faraday, where at the bottom of this image, this sort of strange structure you can see right at the bottom of the picture there is actually a very early form of a battery made up from several not very powerful cells, pushing an electrical current through a wire. And you can see that wire is mounted above a compass. That's an old-fashioned ship's compass designed for navigating on the sea. And as they connect the wire, what they will see is that compass moves. In other words, by the current flowing through a wire, it will create a magnetic field, and that magnetic field will create an effect on the compass. In fact, not just any flow of current, but any moving charges, which is a flow of current, will create a magnetic field. What's this got to do with the Earth? Well, a little bit of geography. The centre of the Earth has a solid iron core, but then there is the liquid outer core, and that core tends to, we believe, have stripped down hot magnetic atoms of iron moving around. So in fact you do have moving charges deep within the Earth, and a similar explanation is why things like the sun have magnetic fields, because the plasmas inside are all moving, so you have moving charges. That doesn't really explain kind of a permanent magnet like the bar magnets that you'll have played with. How do they get magnetic fields? There's no obvious current there. Well, there is at the very smallest scale. The very smallest scale you can get is atoms, and a property of the electrons that orbit the nucleus in an atom is that they have this quantum mechanical property called spin. In other words, they have what's called a magnetic dipole moment. They act like a tiny magnet. Now, one of the things about quantum mechanics is that it doesn't give half measures; it gives ups or downs, ones or zeros, and so magnetic spin of an electron is either up or down. Now, in most materials, these have more or less equal numbers of spin up and spin down electrons, but in certain materials, particularly those about near the middle of the periodic table, that's not so true. And there are a small group of elements, namely iron, but also cobalt, nickel, which can form magnets naturally. And so the magnetic materials that we commonly encounter here on Earth, particularly historically, tend to be associated with large amounts of iron. So within these magnetic materials, the spins aren't aligned, but what will tend to happen sometimes is that some of these atoms will tend to line up with the atoms next to them, and this can build entire regions of the order of fractions of a centimetre where all of the spins are aligned. They're acting like a little magnet. Now, some regions, these regions are called domains, will be lined up one way and some will be lined up another way, and that's what happens in a lump of iron. But if I can persuade all of those domains, or most of those domains, to line up in one direction, then I will have a permanent magnet. Okay, diagram on the bottom right kind of shows this. You have a random arrangement of domains, you won't have an actual magnet. But if I can align all, or at least most of the domains, then I will have an overall magnet. Okay, so here on the right hand side is the same idea. These are the domains before the thing is magnetized. It's still a magnetic material, but after they're magnetized temporarily or permanently, then I will have turned this thing into a magnet. Here is another substance, a neodymium-based magnet, as the formula at the bottom left of the picture indicates. And by a kind of staining technique, you can see these crystals, these grains, very small. Notice the scale there is 20 micrometers. You can see these domains lined up in different directions. So the sort of lighter areas, all these sort of separate things are single crystal grains, but the two different shades line up. The highlighted grain, by the way, is orientated sort of vertically rather than horizontally, so it's like a cross section through one of these other sections. So this is more or less, it's a magnetic material, but it's not actually a magnet at the moment because those domains have not been aligned. This little video, courtesy of MIT, gives you an idea of domains by kind of a simulation. These made up of needles, and you can see it's sort of like these simulated domains are all lined up in different directions. But if I take a magnet, or if the experimenter takes a magnet and gives it a big wipe across the top, then it will kind of mix these domains up, give them a shuffle, and in the end they will tend to align, not all of them, but the majority of them in a single direction, and we have a simulated permanent magnet. Now, Faraday, in that picture above, was demonstrating magnetic fields caused by currents, and so we'll finish off by just looking at what those magnetic fields like. Now, there's a rule here which you kind of need to know. I call it the right hand screw rule because your fingers go a little bit like a screw. So if you take a wire carrying little currents of, this is probably actually electrons, but we're talking about conventional current direction, by the way. So in a conventional current direction in this way from left to right, if you put your right hand with your thumb pointing along the cable, then your fingers will curl around the wire, and that will give you the direction of the magnetic field. So the magnetic field represents these concentric circles in cross section, so concentric sort of sheets, if you like, concentric tubes, showing the magnetic field direction, which are circular, as I say, in cross section in this clockwise if viewed from the left direction. That's what happens if you get a single wire. Now, if you can imagine sort of coiling that wire around into a loop, then your sheets of magnetic field lines will also coil, and you end up with kind of like doughnut effect. Okay. Now, you'll notice that all of the lines at the top are going away from the magnetic field, from the coil, and all the lines at the bottom are going towards, which is a little bit like a magnetic pole. All the field lines go away in a bar magnet, the North Pole, and go towards the South Pole. And in fact, if you take this sort of ring and stack it with lots of other rings, in fact you can connect them, you get something called a solenoid. And now that does look like a lot like a bar magnet sort of field pattern. So on the left, all the arrows are going away, and so our solenoid acts like a bar magnet, with the left-hand side being the North Pole and the right-hand side being the South Pole. The only difference with a bar magnet is that this has a very strong magnetic field inside the solenoid, the coiled wire. Okay, so that gives you an introduction to different types of field lines. Here's another example of these solenoids, and it's showing you the comparison between the magnetic field due to a solenoid and a very similar looking magnetic field due to a bar magnet. In the next video, we'll look at how to actually do some calculations involving the strength of these magnetic fields, how we can calculate the strength of a field based on the electric current and the forces that affect a current or a current carrying wire when we put it in a magnetic field. Thank you very much for your attention.